I'd like to invite the next speaker. Jimeng Shi from Florida International University will be presenting a graph transformer network for flood forecasting with heterogeneous covariates.
Hi everyone, good morning. My name is Jimeng Shi, a PhD student in computer science from Florida International University. Today I'm going to present our work, flood prediction using a deep learning-based model, graph transformer network. First, I would like to thank my brilliant co-authors, Doctors Vitalii Stebliankin, Zhaonan Wang, Shaowen Wang, and my advisor, Giri Narasimhan. Thanks a lot for your efforts. Now let's get started with the introduction of the problem we are going to solve. These two figures show the flooding situation that happened in South Florida and Western Germany in recent past years. From these two figures, we can tell flooding has caused many troubles. For example, it could damage a property, crush the traffic, make the city shut down, or even make the water resources get polluted, and etc. So therefore, flooding is a thing. It's a big deal. We should pay more attention on flood management. In other words, in our work, we aim to mitigate flooding or even avoid flooding using deep learning models. We took the domain of South Florida, which is a coastal system that is highly prone to frequent storms and floods. In this domain, we have some information of the water level that's distributed in different locations in this river, and we also have some covariate information like the rainfall information and the tide information, because this is a coastal system. It has to be impacted by some sea level. Then how could we do some flood management? Well, fortunately, we have some hydraulic structures in this domain. We have some gate and pump which can be used to control the water level in the river. That's a good thing to know, because based on that, one possible idea is to mitigate flooding is before the storm comes, we could pre-release some water from the areas where the rain is going to come to some other areas where there's no rain at all. In this case, for example, if we know there's a rain tomorrow that happens in upstream, then we could open the gate on the top left. Then the water will flow from upstream to downstream, looking like this. In this case, the upstream will have higher capacity to accommodate some more rainwater while raining, and at the same time keep no flooding. So now let's take a look at the workflow of our work, flood prediction and mitigation. First, we have the input of the state of a coastal system. The first step is to predict the floods by predicting water level in the future, let's say some time point. Then we will know the time of flooding, how long the flooding will last, how severe the flooding is. Once we know the flooding information in the future, since today, we can do something. We can take some actions to manage water level in advance by controlling the gate and the pumps in this domain. For the water level prediction, most of current models are physics-based models, for example, high-cross. But the limitation of a high-cross is very slow, especially for larger watersheds in a big domain. So in our work, both steps are achieved by AI models, by neural networks. One advantage of a neural network is once the neural network are trained, we can deploy them to practice, and they will give the output very quickly. I will talk more advantage of a neural network later, but for this neural network, we have many different models, but for our work, we developed a new one. I will talk about it in the next slides, in the next slides. But for water level, for flood prediction, we aim to predict the water level in the future, let's say, k time steps, by considering the input from the recent past of all of variables. We believe the future information can have some impact on the water level in the future. So at the same time, we consider some information from the exactly k time step in the future. The rainfall and tide information can be reliably predicted or estimated by some other models or some weather agencies. The gate schedules in the future is totally decided by humans, so we can operate like whatever we want. Given this, all of this input, we trained a neural network to output the water level in the future. The neural network we developed is graph transformer network. Here, because of the time limit, I don't introduce much details, but briefly speaking, we use different deep learning models. In the top line, we use convolutional neural network and the transformer to learn the embedding information of all covariates. At the bottom line, we use a graph neural network and a long short-term memory to learn the spatial and the temporal information of the water levels. Then, to figure out how much contribution, how each covariate impacts the water level, we use the attention layer to learn this dependence relationship. At last, we output the water level in the future. Here, this table shows some prediction arrows of all of the model with the future information. The last row is our model, flood prediction, graph transformer network. You can tell the arrow is much smaller than others, which means our model is more accurate. The next question is, what if we don't use the future information? If we don't include the future information, the prediction errors will go up a lot. And that means the performance drops. So, which proves the future information is very important for water level prediction. Because of course, you can imagine the information that happens in tomorrow must have much impact on the water level in tomorrow. This table shows the training time and the testing time of all of the different models, including the physics-based model, high-class, and the other deep learning-based model. We don't consider the training time a lot because the training time is a one-time cost. Once they are trained, they just deploy it to practice and use that to generate the output very quickly. The second row is the testing time. Excuse me. You can tell the difference of the test time of different models. The deep learning-based models take much less time, almost reduced by 500 times. So this makes the real-time prediction become possible. Here is some explainability. People always say a neural network is a black box, but what's going on inside? Here we provide some explainability to figure out how much attention between the water level and the other covariate. In other words, how each covariate impacts the water level. There are much details here, but I just point out two. The first one, you can check out the second column. The second column here shows the water level at all locations depends on the water level at S4. S4 is the tide information, which makes sense because this is a coastal system. It's connected and very close to the ocean, so it has some impact by the sea level. The second interesting thing is if you check out each row. For example, if you check out the last row, you can see the water level at 26 pay a lot of attention on the pump at 26. If you check this water level at 25B, the water level will pay more attention on the water level, the gate at 25B, and the pump at 25B. So what I want to say is the water level at some location pay lots of attention on the same location, on the nearby hydraulic structures on the same location. Because that makes sense, that's consistent to our prior knowledge, which means we can prove our deep learning models are learning the correct and the useful things. We also use some explainability tool to visualize the computation, to visualize the contribution values from each input variable, each input time step to the final output. This is a heat map of contribution values from each covariate to the future to the final output. In our experiments, we use a past window of 72 hours and to predict the future 24 hours. What we could learn from this figure is our model, the tied information from the future 24 hours have the most contribution to the final output. Because again, this is a coastal system, which again prove our model are learning the correct things. There are also some interesting things. There are some pattern for this gate information here. But why is that? To figure out what's going on here, we visualize the observed data in our original data set. You can see this contribution values happen only when the gates are opened. That makes sense, because if you open the gate, the water levels will change because the gate opening and the pump opening from the upstream or downstream. We also want to know how much the water level from the recent past the impact to the future to the output. So here is the water level in the past 3 days, 72 hours. The model tells us the water level from the recent past have more contribution than the far past, which makes sense because you want to predict, let's say, next week. You don't have to consider the thing happened in last year. Maybe just focus this month or the past 2 weeks. So the good thing is we compute this model explainability or the contribution values, which can prove our deep learning models are learning the useful and the correct things. It's a kind of white box, not exactly the black box. Here are some important conclusions. First is the future covariate information. If you include it, the performance will become better, which proves this is very important. The second one is water level in this coastal system rely on the tide information from the future and the water from the recent past. At the same time, it also depends on some hydraulic structures nearby, the gate and pump opening. The last one is the most interesting one. Deep learning models have some more advantage. For example, it could perform much faster. It could perform more accurate, than the baseline models in this work. And it can provide more interpretable results, which can help us to understand this domain to, at the same time, to validate, to prove the deep learning models are learning the correct things. That's all for the flood prediction. We also finished the work of flood mitigation by this framework. But today I'm not gonna present this. You can have a quick look if you are interested. We can discuss the more details. We also wrote 2 manuscripts about this work and submit to some machine learning conference. They are in under review. We also looking for the collaborators who are interested in this methodology, and we want to scale this methodology to much larger watershed, the domain, to validate the efficiency and the effectiveness of our method. All right, thank you.